already. So, but this operator doesn't have this, so this is not Hermitian, and also this operator, for example, partial x is not Hermitian. You can see. For example, one of them I want to show that. So, for example, I want to show that operator minus h power partial x. This is Hermitian or not? I just write this equation. No, let me, I will write. You need to specify. So I take the integral very, very general from entirely space. So now I needed to make integration part by part. So I take the integration part of that minus h power phi star psi from minus infinity to infinity minus plus h bar yes, this is just partial. Integral u dv is uv minus integral v du, nothing new. But you have this term, what you need to do with that? You see that? Having the operator and having the definition is not enough to check the operator is Hermitian or not. You need to have more information about that. So here we normally we skip by that. We say that these functions are indicate in the way that when x tends to the infinity, we suppose that they are converging or they are decaying or not, finally they tend to the zero. Like that. But is it correct for any functions? No. For example, this function, take this function. Do you know what is that? E I x? No, what is that in the quantum? What does it mean, this function? No. This is the wave function for the free particle in quantum mechanics. When there is no potential, this is the solution of Schrödinger equations. For this function, you take x minus infinity or plus infinity. What you obtain? Nothing. Exponential of the complex number, when the complex number, the real part tends to infinity or minus. It's nothing, just oscillating until the end. Eternally oscillating, huh? Forever oscillating. No, never tends to zero. Not only the definition, also you needed to have, so this such function, you cannot use it this year. Technically, they say that they are not normalizable, real normalizable. This is the only and the last problem in quantum physics which we cannot find a satisfactory solution for that. Why the free particle is like that? Why the free particle never can have the convergence over wave function? I mean, why it's not normalizable? And this is one of the tough questions. Anyway, if you suppose that, you can forget about that and look at that. What happened here is that I can take this h bar here and rent this star for that also. Can I write that? I insert this inside the bracket and I give it minus, but I also give it the star to the whole. So I did nothing because star of minus 1 is ours. And this is the definition. So you can say that this operator is Hermitian. In modern language, we say that. In modern language, this is the translation of these integrals. These integrals are very lengthy. So, for example, just imagine if you want to calculate in nuclear physics, if you want to calculate the transition amplitude for some nuclear processor, anything like this Musbar effect, like anything else you want to do. So any calculation in nuclear physics, you have a lot of this expectation value. So if you want to write all the integrals, it will be very confusing. So they use this notation of integral. So it was in the bracket, so it was not our task. Our task is just to study this. I told you, this is the definition of the operator in Heisenberg friction. I want to back to this. So that was just a simple calculation. Can I remove it? Because I don't want to keep it here, because it was just in the bracket. So, okay, this is the, okay, now I will ask you, what is the time equation evolution for this operator? I mean, what is the dA dt? This is the time evolution equation for this time evolution dynamical equation for this operator. So I want to take the time derivative. Just take the time derivative normal. What you did, what you are doing. I T H bar E I.
Without.
Yeah, without. Yes.
With H.
H A0. No. Maybe Schrodinger operator is also a function of time. Who knows that? Maybe this is explicit.
Then at the
implicit.
beginning there is minus.
No, I take derivative from that.
Oh,
Now I will reach this point. This. We are very lucky that here you have edge and here you have a function of the edge. So very safely I can pass this from that. How you can do that? Normally in quantum mechanics you cannot do that. I mean in quantum mechanics AB is not BA. But there is exception here, is that this is the edge and this is a function of edge. So they have the same sense. So they can pass from each other, huh? Because they have this edge and function of edge. If it was something else like the spin, momentum, x, edge. And that will help you to, and look.
In the middle one, dAs over dt. If we assume that's A0, should it be constant or not?
No, you can set it as 0.
Because time is 0.
Sometimes the operator is implicitly time dependent. Like you have a magnetic field and the magnetic field is a function of the time. Your Hamiltonian, I know it's Hamiltonian at the time is 0, but the magnetic field is changing by the time. So how you can do that?